Hello and welcome. In this lesson, we'll explore the key features of logarithmic functions. We'll focus on three main concepts: the meaning of the word logarithm, the features of the graphs of logarithmic functions, and some basic properties of logarithmic expressions. So let's get started. The meaning of the word logarithm. Logarithm, as a matter of fact, is just another name for exponent. For example, when we say 2 to the power of 3 or 2 to the exponent 3 equals 8, one way of reading this is 3 is the exponent we must raise the base of 2 in order to obtain 8. And since we said that exponent and logarithm have the same meaning, we can read the same statement as 3 is the exponent, this time we'll say the logarithm, we must raise the base of 2 to obtain number 8. Now let's convert this sentence into a mathematical statement. So we said that 3, in mathematics when we say is, we mean equals. The logarithm, so for the term logarithm, we're going to use the symbol log or all three lowercase letters. So that's an acronym for the word logarithm. We must raise the base 2. So at the bottom of the word log, we're going to write number 2, which indicates that 2 is the base, to obtain 8. Now, any exponential expression can be written in logarithmic form and vice versa. And I hope you are as excited as I am to take a look at some exponential statements and convert them into logarithmic statements and vice versa. So let's take a look at the first group. So we have expressions in exponential form. So we'll start with the first one. We're talking about logarithmic expressions, so our focus will be on the exponent or logarithm. So we'll write 3 is the log. We must raise the base 5 to obtain 125. Next, the exponent is c. So we'll say c is or equals the log. We must raise the base b to obtain a. Next, x is the exponent or the log. We must raise the base 3 to obtain y. Next, x is the log. We must raise the base 2 to obtain y. In the next set of exercises, we have logarithmic expressions. We need to convert them into exponential expressions or statements. So remember that this will represent the log, right? And log or exponent means the same thing. We always start off from the base. And we're going to say that the base of 3 raised to the power or exponent, or should we say log, right? To the power of p equals 7. Next, the base is n to the power or exponent or log, say it whichever way you wish, equals p. Last, 7 is the base, exponent or log is 2, equals 49. Next, we're going to take a look at the features of the graphs of logarithmic functions and their transformations. And before we do that, we'll do a quick review about inverse functions. You've done inverse functions probably in grade 11. I will try to refresh your memory one more time about inverse functions. We said that they are reflections of each other about the line y equals x. Y equals x is a straight line that crosses the origin, makes an angle of 45 degrees here, okay? And when we reflect, when we reflect a function along the line y equals x, we say that the coordinates of every point on the given function will switch around, if you remember. And let's take an example. For example, if we had here a point A with coordinates x equals 1, y equals 2, and we were to reflect this point about the line y equals x, it means that we have to draw a perpendicular line. That's how we draw the reflections, right? Any kind of reflections. And we have to pick a point on the other side of the reflection line, same distance from it. We'll mark this as point A prime. Now the coordinates of A prime, if you notice here, will be x equals 2, y equals 1. As you can see in here, the x of A became the y of A prime, which is the image point on the other side of y equals x, and the y of A became the x of A prime. And that's what we mean when we say that in inverse relations, x becomes y and y becomes x. So the domain and the range interchange. So we're going to say that inverse functions are reflections of each other about the line y equals x. And the reason why we started off with inverse, or the definition of inverse relations, is because, as a matter of fact, again, logarithmic functions and exponential functions are reflections of each other along the y equals x line. So how does that happen? Consider the equation, the exponential of the exponential function y equals 2 to the power of x. We are going to build the inverse of y equals 2 to the x. Remember that to find the inverse of a function, we need to follow two simple steps. Step 1, we switch x with y. So when we switch x with y, instead of y equals 2 to the power of x, we'll have x equals 2 to the power of y, which I kind of wrote in here as well. But let's continue here. Now we're going to write this function as y equals, in terms of x. So we're going to say y is or equals the log. We must raise the base of 2 in order to obtain x. So in other words, we converted this exponential statement into a logarithmic statement. And this is what we obtain, y equals log with base 2 of x. Now, this is what we call a logarithmic function with base 2. And what we're going to do is draw both graphs on the same grid. I'm going to get started with y equals 2 to the power of x. Let's color code them. And we know that y equals 2 to the power of x. We're familiar with this graph because we just did this in lesson 1 of this unit. The y-intercept is at 1. When x equals 1, y equals 2. When x equals 2, y equals 4, 2 squared. At x equals 3, we have y equal to 8, 2 to the power of 3. At x equals -1, we have the y value of half, and then the rest of the graph will continue towards the negative x values, approaching, I'm not very happy with this shape here. Let me make it better, just because we can. There we go. And on this side, as x decreases, the y, or the graph, will approach the x-axis, or the y values will approach 0. So this is y equals 2 to the power of x. And now we're going to draw the line y equals x, which is the reflection line. I'm cheating here a little bit. I want to draw the line. Okay, I'm going to make it as long as possible so that we have a clear view of the inverse function. And now we're going to draw the reflection of y equals 2 to the power of x. Now let's take a look at every single point in here. So we had x equals 0, y equals 1. This will become 1 and 0 for the inverse because the coordinates have to switch around. Now, here we have x equals 1, y equals 2. That means that our next point would be x equals 2, y equals 1. X equals 2, y equals 4. So this will give 4 and 2 for the inverse of the exponential. Next we have x equals 3, y equals 8. And this will give 8 and 3 for the log function. One more point, x equals -1, y equals 0.5. So negative 0.5 and, here we go, 0.5 and negative 1, 0.5, negative 1, 0.5. So this will change to become 0.5 and negative 1. So let's draw the graph. Wow, this is beautiful. So here we go. We have the graph of y equals log with base 2 of x. So as you can see, these two are reflections of each other. And we're going to say that logarithmic function is the inverse of the exponential function because that's how we obtained its equation. Now we will compare the two graphs. So let's take a look at the domain. We said that the domain of exponential functions is x, any real number, because we can give x any value and be able to evaluate y. For the range, we'll say that y has to be bigger than 0. Any real number, but bigger than 0. The graph is all above its horizontal asymptote, which is at y equals 0. There is no x-intercept, but there is a y-intercept at 0, 1. So there is the y-intercept. And the graph will never touch the x-axis, so no x-intercepts. And there is a horizontal asymptote at y equals 0. Now, let's take a look at the inverse of the exponential, which is the log. For the domain of the log function, as you can see in here, the graph is all to the right of the y-axis. So that means that the x values are bigger than 0. The range, on the other hand, you can see that we have negative values of y, we have y equal to 0, and positive values of y, which means that y can be any real number. Let's take a look at the x-intercept. So we see an x-intercept right at 1, so we're going to say there will be an x-intercept at 1. We can say x-intercept equals 1, same idea. There is no y-intercept because the graph will never touch the y-axis, so therefore we're going to say none. And there is an asymptote, that would be the y-axis, and the equation of the y-axis is x equals 0, and it's a vertical asymptote. Now, if we take a look at the table here, you can tell that the domains have switched, right? So the domain of 2 to the x has become the range of the log. The range of 2 to the x has become the domain of the log function, and vice versa. So for the exponential, we have no x-intercept. Here we have no y-intercept because they change roles. For the y-intercept, exponential function has a y-intercept at 0, 1. On the other hand, log functions have x-intercept at 1, 0. Exponential functions have a horizontal asymptote while log functions have a vertical asymptote. Now you're probably wondering and thinking, why do log functions have a vertical asymptote? And I want you to think about it. Now remember where the x values are in the log function. So the x values are inside log, and what sits inside log? What sits inside log is an exponential number. Remember when we said 2 to the power 3 equals 8, which means 3 is the log with base 2 of number 8. So number 8 has the value or the power of a logarithmic, of an exponential number. And an exponential number with a positive base will never be negative. So when the exponent is, say, for example, negative, it will be a smaller decimal, but it will never become a negative number. And that is the reason why the domain in exponential functions will always be all the positive numbers and will have a vertical asymptote, because x will never equal 0. Because when you think about it, if we had the log with base 2 of 0, it means that we need to find some exponent that will give the base 2 a value of 0. So it will make this exponential number 0. And this is not possible. So we cannot actually figure out any power or find any power such that 2 to that power would be equal to 0. So I hope this made sense. We're going to take a look at some properties of logarithmic expressions. Before I move on, I just want to mention one last thing about logarithmic functions. As a matter of fact, the logarithmic functions will undergo the exact same transformations that any other function out there undergoes. So, for example, it will transform. So if we have y equals log with base 2 of x as a basic exponential function, then we'll say that the transformations will be described by the equation a, which is the coefficient for the y values, log with base 2, k will be the coefficient for the x values, x minus d will be the translation, the horizontal translation, and then plus c, which is the vertical translation. So this would be horizontal and vertical. And all the transformations are applied in the exact same way as in any other function out there. We're going to take a look at more examples in the next lessons or in the practice questions. The third concept for today is some basic properties of logarithmic expressions. So this is probably the more fun part of the lesson, because it kind of brings together the functions and the meaning of the word logarithm. So, number 1, the logarithm with base a of 1 would equal 0. Why is that? So we are going to explain this by converting it to exponential form, because we understand exponents a bit better. So a is the base, so we'll say a. 0 is the log, or the power, to the power of 0 equals 1, which is the exponential number. Next, we'll say that log with base a of a to the power of x equals x. And I will color code those letters in the statement here. So I'm going to make this a in here pink. So we'll have a green and x pink. So the reason why is because the base a, that green base, raised to the power of x, that pink x, would equal this exponential number here, a to the power of x. So as you see, both sides are equal, which makes this statement true. Last, we have a to the power of log with base a of x equals x. So I will focus on this exponent here. And I will say this exponent, whose name is log with base a of x, is actually an exponent, or which should we say log? Exponent or log. We must raise this base a in here in order to obtain x. So as you can see here, both left and right side are equal, and they were built based on the same statement, which makes this statement true. So let's practice these properties by in the examples below. Before I get started, I actually wanted to mention one last thing. Remember that when we simplified or worked with exponential numbers, we talked about exponent laws and exponent properties. So the exponent laws were product, quotient, power, which we will revisit in the next lesson. And exponent properties actually explained these little details about exponential numbers, such as a to the power 0 equals 1, okay? Or a to the power of 1 equals a, for example, etc., etc. It changes up a little bit when it comes to logarithmic numbers, but this, what I'm trying to explain in here is that besides the laws, there are properties to exponential and log numbers, and these are the properties of log numbers. So let's get started with some practice questions. We have to find the value of x in the following examples. Log with base 2 of 1 equals x. That means that the base of 2 raised to the log or power x, exponent x equals 1. And now we're thinking, what can x be? So we can make both sides into exponential numbers with base 2 and power 0. And then we have x equal to 0. So we use the properties of logs in this case, or we can use the properties of logs, because we'll know that log with base a of number 1 will always be equal to 0. So you can also find the answer or state the answer right away based on the properties. Next, we have log with base a of a to the n equals x. That means that a to the power of x equals a to the power of n, which means that x equals n. Again, just to clarify one more time, this is the a in the base raised to the power of x, which is the log, equals the exponential number inside the log. Next, we have a to the power of log with base a of x equals y. So we're going to say that in this case, we have a to the power of y, or let's put it this way, it's easier. So start with log with base a of x equals, so log with base a of x is in the spot of the exponent again. So the exponent would equal, we can also call it the log, with base a of number y. So we're going to say that everything looks the same in both sides except for x and y, and since the two terms are equal, we'll say x equals y. Now, before we leave, one last note. If you look at the calculator, your calculator will have a button that says log. And it may or may not show the base in the log. Obviously, we can have logarithmic terms of different bases, just like we have exponential terms with different bases. And the calculator, by convention, has a base of 10. This is called a common logarithm. And we're going to learn how to work with it in the next lesson when we learn how to evaluate a logarithmic expression. But if you remember, when we had, say, for example, a term, x, with no exponent, we always assume that the exponent must be 1. Same thing with log with base 10 of x. Since this is base of 10 is a common base, if we see that an expression contains simply log x, it means that the base is 10. We just don't write the base of 10. So both ways, we're going to say that 10 is the common base, the same base the calculator uses in the calculations with log. And when we don't write the 10, it means that the base must be 10. Same as when we don't write the power of a term, it means that the power is 1. So it's a similar idea. So again, I would like to thank you very much for choosing to listen to my lessons. Leave me a comment on the comment section. If you have any questions, I'll be very happy to answer. And thanks again for choosing to learn from me. Bye for now.